Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, good morning, everyone. It's my great pleasure to have Professor Min Do here. Professor Do is Associate Professor from the Department of Electrical and Computer Engineering at UIUC. He has received numerous awards, including a Career Award from NSF, a Young Author Best Paper Award from IEEE in 2008. He was named a Beckman Fellow at Center of Advanced Study, UIUC, in 2006, and a Xerox Award for Faculty Research for the College of Engineering. He's also a co-founder and the CTO of Nuvix, how do I spell this?
Yeah, Nuvix.
Incorporation, a spin-off from UIUC to commercialize depth-based visual communication. So without further ado, let's welcome Professor Do.
Thanks. Thank you. Thank you very much. It's my great pleasure and honor to be here. This is my first time visiting Microsoft Research. I always admire a lot of work's been coming out from this place, and it's a great pleasure to connect with some of the old friends, as well as see some person that I only know through papers and publications. So. And certainly, it's resonated a lot with the recent activities coming out of Microsoft. I think now Microsoft is really truly the center of the universe surrounding the depth, sensings, and how to use this for immersive visual communication. So again, it is a great time to be here, and I hope we can start up some collaboration and some discussion afterward. So this is something that I've been working at the University of Illinois for almost 10 years now. And my original background was in developing high-dimensional wavelets for image representations. So, can tackle problems like compressions, denoising, and so on. And about 5 years ago, I get very interested in the depth cameras, the technology that can provide additional to typical color image that we as an image processor would deal with. Now we can also have a very different type of visual information, namely the depth information. And a very intriguing question to me is, how can we provide different techniques to exploit that new type of data? And in particular for the visual communication application. So let's first start with, so this is something that we was dream up in 2005 about, a vision that, can we extend beyond televisions that are typical visual communication where we only have a single fixed camera recording the event, the persons, and then the viewer just simply passively stay still and watch the content. But can we, for example, very nice pleasure to be here, and we can move around, talk to people. So the freedom, not just having a fixed camera, but I can walk around and see information in two four-dimensional, 3D in space and 1D in time. I think certainly it is a very big freedom that we can enhance. So what does it mean? So there is a picture actually drawn by someone here in the audience, Matt, who is my former PhD student at UIUC and now working at Microsoft. The vision that what we was very excited at that time is we can have multiple cameras recording a dynamic environment, a scene. And then we would do a lot of very interesting advanced signal and image processing that packetizes information, have a very efficient representations, and then transmit that across the network or storage so that later on or live we can view the information individual persons or different sessions, we can view that at different viewing angle, different perspective, different positions. So that was the dream, and this is a setup, but as you can see, it can be manifest itself in many different other applications. For example, how can we generate a stereoscopic stream, right? For example, we can record the views, and now people are looking at the auto stereoscopic display, which then you have to synthesize multiple views. And we only have a limited set of recordings, so now you have to synthesize those views. So that's one. Also, if you take the person out, you want to extract and change the viewpoint slightly, for example, do some eye gaze corrections. All of these problems, I think it is, to me, fundamentally a problem of view synthesis using live recorded data is going to be an exciting problem. So the vision, which, again, get us very excited about is existing audio-visual communication still only use a single camera, very little processing, and the viewer just stay there passively. So as we look, the future, if the cameras, the sensors getting very, very cheap, and we have a lot of computing power, and bandwidth available to us, how can we provide a new viewing experience? And I think that's very exciting research problems. Why? Because in the middle of that is how can we develop new signal processing theory and algorithms to capture this kind of new setting and deliver new experience. So shortly after we decide about this problem, and now it become such a very exciting time for us, is there's a new kid on the block that provide not just simple, not just regular camera that have a color information, but then there's a new type of sensing capability that can measure in real time video rate, depth information. So that provides additional information, and this device now, as like Connect, is going to reach the consumer space, with low cost. So again, how can we exploit this to deliver this visual communication experience? And again, I'm fully aware that it's also something that's very actively researched and done here at Microsoft Research. So I'm coming here to learn and look for the new opportunity to collaborate. So let's first look at, again, my background is signal processing. So, first we look at the image, we look at the signal. And one of the things, so that one example of the depth camera, we have one of these, when we start several years ago, it was a very expensive, it's like $10,000 PMD camera. And that's why, now we're so excited that, with the same amount of money, we can get hundreds of those Connect camera, then play around with them. But the fundamental problem there is the depth information tend to be noisy, have a lower resolutions, and there's some of the occlusion problem here because of the way the data is measured. So, you can zooming in, again, you see those very important problems there. So, again, as someone been working on image and video processing, dealing a lot with linear image, now it's a very different type of data, right? This is a new linear here, and I'm drawn to it because of, okay, what are the processing algorithm we can develop on here? So now go back to the vision that we set out early on. Can we generate multiple viewpoints, free view video based on some fixed recording? So let's make the thing concrete. I'm going to start, setting and look at the problem in the following setting. So we're going to have a fixed set of cameras. There's a two color cameras, and in the middle we put a depth camera. And we're going to record a 3D environment, right? A dynamic 3D scene. And then based on this recording, we want to use a small number of cameras so that it's very efficiently transmitted over the internet or store. We can synthesize, we would like to synthesize an arbitrary view, and if we have a time, we can freely move around here, or if we can have synthesize them as a stereo pair, then we can look at this environment in 3D at any viewing angle So that, and we want to do it fast. So that is a concrete setting. And when we look at these problems, and again, we can extrapolate, what are the key challenges. One is the depth cameras that we deal with that time, they tend to have very low resolutions. So now how can we couple that with the existing, available color image with high color quality, high resolution? So that, combining that's going to be one key issue. And, we're interested in the setting that, camera can be dropped in very easily without, very complicated calibration techniques. So the user don't have to, the camera don't have to become in the integrated system, so that it can be individual units. And the next one is at that time also parallel computing, which now become the mainstream is how can we deploy these kind of computing algorithms in a parallel platform so that we can have real-time high speed up. Okay, so let me jump in and explain our algorithm, which borrow ideas from many different techniques, and it's just our attempt to develop and deliver some of this free view and then set up that as a framework to analyze the quality of the possible reconstructed image. Okay, so again, here the setting. So we have a one depth camera in the middle and two color camera. So the algorithm is a very trivial. First, because we have the depth information, so we can go back and then we can synthesize, warp the depth information from this middle one to this two color camera. Now, after we do that, again, the subtle point why we did that is because then now we at those color camera position, we have both color and depth. And now because we have that, we can exploit the rich, high resolution, high quality of this color image, to have own sort of problem with occlusions, low resolution in these warp depth images. Right? And then based on that, we do those processing and provide a very high quality depth image here. So again, hit that key point, how to combine depth with color. And when we have this depth information per pixel at those color camera, then we can do a back projection here and warp and synthesize the visual novel viewpoint. Okay, so that's the three steps. And again, we purposely think about how to map the whole thing into a GPU so that we can utilize all sort of hardware acceleration that provided with GPU. Okay, so again, my background is signal processing, so I'm interested in first, this is a processing step. So let me walk through this set of sequence of processing steps that was provided to combine the depth and color image into a high resolution depth enhanced. So first, if we remember, the first step is we take a depth from a fixed point and we warp them to the color point. And the depth we use is a very low resolution, so you can hardly see. So what you have is a very sparse set of point cloud, and the color, they are color coded here, so that they show I think the darker color, the closer the object, and the vice versa. But then what we know because of those points, and we know that which object is closer than the other. So then we can eliminate those the white point here have to be occluded, from those darker points. So then now we simply do this occlusion removal, and now we have this more accurate set of point cloud representing the 3D scene in front of us. But still, it's a very poor quality. So now combining depth with color, that's where the power coming in. And one of the very popular techniques, again, we picked this one because we can then map them to GPU very fast. And we'll show some number later. We quickly get interpolated, few in terms of holes and higher resolution. But again, you see that a lot of this is a problem still here. Again, I was trained as an image processors, so to me, the best way to explain an algorithm is to go through the sequence of, intermediate steps. So the detail of those steps, later on I would show the reference and you can look into detail. But let me just go through these images as, try to deliver the point. So the next step is, again, we still have those big holes in the middle because of the occluded. So, obviously when we draw them in this sense, we know that this part have to belong to the background. So we know that, that is the background, and using certain just simple 1D extrapolations, that we can look at the epipolar line and we can extend them out and we can fill them. So that's another step, and now we can fill them in. Without doing that, if simply just filling this hole is just average or interpolate, then you can smear them out, right? But with a little bit of understanding about what is a 3D object underlying the scene, because now we know the depth information, we can do a better job in filling this occluded area. Okay, now after that, one thing we learn is for the depth image, frontal view, we have a very sharp boundary. But as soon as we move away that view, then there's a term now people call it the flying pixel, which is a pixel that between the foreground and background, and that when they measure depth, it get average. So that hang out in this is along this line here, and they have very poor quality. So when you warp them over, these ones show up. So we have to develop something that can clean up this. And if you look at this, first, my students show me this, said, how can we clean up this? It's a really, hard problem. But then we realize that if we have a color information next to us, because we have some, very nice color image here, then we know exactly at that viewpoint how we can find out the edge so that we can, do this processing that eliminate where's the background, where's the foreground, where's the, in-between pixel. So, with that, then we can do some, very simple trick. Again, some very simple and efficient techniques that can give us this clean image. All right. So the example result, again, is not perfect because you can still see some of these artifacts here. But what it shows here is, we take two images and the depth in the middle that has poor resolutions. We can synthesize a high-quality depth map. And then based on that, we can render image at a novel viewpoint. Here another perspective here. Okay. And here's a video that we can fly through and see the object. Again, we can synthesize any view, so you can see them as a we can synthesize a stereo pair, and we can see things in 3D. Okay. And all of this can be done in real time. Because I will show there's a number that we map that efficiently into GPU. I have some of my colleagues in really good class expert in CUDA, and they help us to map that into a GPU. Okay, so as you can see that in this sequence of steps of the algorithms, and then one thing that we've been looking at too is, well, can we quantify accurately what is the error that could result from this set of processing steps in synthesizing the final image, and using that to maybe give a prediction, what the best configuration of the scene, how to, in compressions, I have a depth and color, how to best allocate bits between depth and color to deliver the final high quality synthesized viewpoint. So that is a problem that we like to analyze. So, and of course, now we switch gear now to, try to analyze it, and then, we have to do a lot of simplification here so that it's we still make the problem tractable. And we use the framework of the propagation algorithm I just described, and look at the simplified version of that. Okay, so let me look at a very simple setting here. First, just try to deliver the point. So imagine that we have some surface, some object in 3D, and we, at this viewpoint here, through propagation, we have a set of depths corresponding to this camera and the color pixel. Okay, so we have that set. And now we want to synthesize the new viewpoint based on a set of those per pixel, depth per pixel viewpoint. And we can set the, we can, we can develop the, the setting which is, certain functional surface. We throw in that the camera have a certain resolution, the depth and texture and texture of the color image have a certain accuracies. This thing, again, it was based on my training is let's say we do a coding with a certain bit rate, and here's a certain distortion, so we can quantify that. And now, given that, what is the best way to deliver a high quality image? The classical problem of, let's say, rate allocation. So, given that setting here, let me give you the gist of this approach. So here is our actual image, one single actual image, and here's our virtual viewpoint where we need to synthesize the color image. So what we do is we take this pixel, we know the depth, so we know that along this ray of light where it is, and then we hit the surface, and then we warp them back here. So now we have a color pixel over here. Now, what happened when this depth is noisy? So we would go out somewhere. Depth noisy would either due to noise from the measurement or noise from the quantization due to coding. It go up somewhere here, and now we warp back. So now the pixel now get move over here. Okay, so that is, we can quantify what is that zeta, right? And the simple geometrical argument, we can bound at that. The next thing is now we look at the virtual viewpoint. At the virtual viewpoint now, we have a set of pixels here, and the ideal function we want to reconstruct. Let me just point here. The ideal function we want to reconstruct is here. But instead of having the pixel here, due to the zeta warping, we have those pixels, and then we have the measurement here. So the noise coming in two parts. One is the zeta now, it gives you the wrong location due to the depth measurements, and then the other one is due to the color. So then you have this. And given this new set of points, we just do a simple interpolation, right? Do a simple interpolation. Here we show using linear interpolation, but the technique, let's say you can pick up your favorite spline interpolation, for example. We can bound that. And then we can bound what is the error of this reconstructed image with the underlying original image. So we can bound that. The next thing is now, remember that we don't just have one actual image. We have a number of them, and then we would go to the 3D scene and we propagate back to a virtual viewpoint. So we have a collection of those, and they we can use a random argument to characterize what the density of those functions, the sample point. It turned out that we can write that as a closed form formula, and put all of those things together. Then we have a final bound on what is the we can characterize. It's a very classical technique in randomized random sets. What is the moment of those different sampling interval after we take those points, we warp over here. Okay. Even though it look very hairy, but actually we can, at certain case, we can compute exactly those numbers. So given that, then we can put together now, and we can find exactly what is the error when we do the reconstruction, and it number of terms here. So let me explain. So first is this one here is telling us how smooth the texture of the scene, right? So of course, if the texture is very smooth, then the error would be small. The other one here is this one here is fully depending on the configuration of the camera and the scene. And then this is the error due to the measurement in texture and then the measurement in depth, and they all warp into this. So that, and all of this terms here we can work out as a closed form. Okay. Now, of course, the question is, okay, I just explained exactly what those terms have to be. So, again, recap here. This term, encode about the geometry of the cameras, what is the scene and how we place the cameras. The number here is telling us about the sampling densities of the, either pixel, color, or depth. And other term, decoding about what are the accuracy of depth and color measurements. So again, this is giving us a symptotic analysis, and we can have a sense of, well, if I'm going to improve the technology, how the error, how the reconstruction error going to behave as we get better accuracy. So even though that is a very messy formula, but actually in a certain case we can find exactly the closed form and you can plot them out. And again, what I'll go here, trying to make the problem tractable, we aim to look at the what is the asymptotic behavior of this setting. So here is a scenario which we have several cameras putting along a line, and we want to synthesize the intermediate viewpoints. Then, for example, our theoretical prediction is how the error is going to behave as we have more and more samples, right? Then, and we can synthesize the scenes. We have everything exactly set up. Then we can measure actual error that have to be, and you can see that it follows very nicely with this theoretical bound. Again, it accurately reflect what we predict that, for example, in this case, the error to decrease linearly as the number of samples increase. Of course, we can extend that to 3D, by using, or we can also extend them to when there's certain occluded areas, and we can know that those are boundary, and we can also, add in some additional terms. Okay, so the main idea here, I guess, is we coupling a particular techniques method to synthesize the viewpoint, and we want to quantify what is the accuracy of the reconstructed image based on the scene configurations, based on the characteristics of the cameras that provide to us. Okay, so the next part, and I promise this slide a little bit out of order. The timing we deal with is, for example, we pick particular this algorithm that if we run in CPU, it would take a lot of time, but very efficiently mapped to GPU because of the parallel architecture. Then we have that saving, and but certain algorithm would not give us that big saving. Overall, certain component we put together, we can achieve real-time rendering. Okay, so that was some 2007, 2009, some of the initial algorithm, and if you notice carefully, the data that I showed early on was a completely synthetic data, right? We have a depth map, we synthesize, well, we have a 3D model, we synthesize what the depth map had to be, and then we do the reconstruction. So now let's come to the real thing. The real thing come later because of when this camera become available, and when we can afford to buy them. So we go ahead and have this simple setup here in our lab that have a depth camera here and have a multiple number of color cameras here. Someone in the room know that he construct part of that setup. There's some footprint here. And then, when we have these images, the problem we try to do here is simulate the algorithm that I described earlier. So, namely, I use input is A, D, and B. And I want to synthesize what could it be at C. Okay? And so, everything is real, and then we try to set up and try to run the algorithm. So, again, here's one of my students. There's a 3 input, 2 left and right, and the depth in the middle here. So just show the result quickly here, left and right, and here's a random view, here's the ground truth. Now, why this is an important problem? As you can see, the goal here is we try to be able to track where the eye gaze could be, and then want to synthesize the view that the person looked directly into the camera. So you can see both of these original viewpoint a little bit off, but then we can synthesize the person as look directly on the camera. Now you can also recognize certain error here along those boundaries, and I would later show where it comes from and how can we deal with them.
Is he wearing something? Is it hair?
Yes.
Is he wearing something or is it hair?
He will wear hat. Okay, so everyone recognize that the depth camera we use at time is very bad with the IR reflection. So human hair tend to absorb a lot of IR. I know the Connect camera now, there's some better feature. But for that camera, for example, dense hair, a lot of pixels get missing. So that's the way we cover up. All right. So again, just a sequence of steps on how we process them. So we propagate the depth, we remove them. We after having this a very coarse set of point cloud, we can synthesize a higher quality depth, and we can fill in the hole by doing this occlusion filling and edge enhancement. So we end up with a much higher per pixel depth quality here. And then when we synthesize view. Now, the nice thing about this is because we have this, then the part that we have along the edge here, we can easily move out, and now we extract the person out from the background. Some of those artifacts I think is due to the compressions. Okay. So that is how we could do a real image and understand that when we map the actual depth maps from a actual depth camera into other color viewpoint, and then each of those color viewpoint now they would have fully per pixel depth plus color. Okay, and we strongly believe that that would be a very efficient representation of the data that with this data now we can ready to transmit and send them or store them somewhere so that viewers either remotely or later in time can quickly view the scene from different viewing angle. Okay, so now come to the next problem is how can we, yes?
Do you allow the same pixel to have multiple depths?
No, we assume that it's only one depth per pixel.
So when you synthesize a new virtual grid, if you just rely on depth, you still have the whole filling.
Yes, so the whole filling we realize on, let's say we don't have one view here, but we have multiple views. At each view they have a per pixel color and depth. So we
need multiple depth cameras.
We either we have one single depth, multiple color, but then we propagate them and do processing, and now from one depth camera we can synthesize multiple depth viewpoint. And if it says occlusion, but then we have a color, so we can fill in those occluded area.
It's just not going to cover them. I don't think it's going to cover them all. You're going to miss a lot. Because the two cameras will also have occlusions to each other, right? Because the many places where you kind of see both color cameras. So the places where both color cameras can see is also limited. So then it's kind of hard to propagate it to everywhere as well.
Yeah. So okay, maybe let me try to understand the point here. So when we first propagate and warp them over, we have a lot of those occluded area, but let me clarify the setting here. So how can we okay. Oops. So the setting we have is one single depth camera, and we have a two color camera, two viewpoints. So first we use propagation and get the two depth here. And of course they have each of those have a lot of those occluded area. But the key thing we have is at this faraway viewpoint here, we have a color information. And we use those information to guide how to fill in those occluded area. And then we now, per color viewpoint here, we have its full depth that's been,
You mean for each camera view, for each color?
Each color, yes.
But what about the view in between? The views in between?
Oh, the view in between, it does, yeah.
We have new occlusions.
So we limit that the view in between that, have to be, any pixel here have to be either seen by one of these two cameras. So, we limit what the freedom of this virtual view can be.
So I'm saying that if you want to free viewpoint, you move your view around, you can make the new occlusions because those viewpoints may not be covered by either color cover 1 or depth cover 1 or color cover 2.
Oh yes, a certain case, let's say you have something like cell occluded area and yes.
So you cannot fill them all. That's what I'm saying.
Oh, I see. Yeah.
Well, if you put your eye exactly at D1, it's okay, right? If you put your eye maybe exactly at C1, maybe it's okay.
Right.
Once you shift off, which happens.
I see.
So then you cannot. You always fill.
I see. Yeah. We was thinking about we have a simple concave surface here. So let's say we look from here, this angle, certain part here get occlude, and we have here now the total union of this.
You would really need to know. Oh, this is a sphere.
Sphere. Yeah.
Nice.
Or let's say I think maybe we have a object as there is a convex surface, for example. Yeah. Yeah. Good point. Yes. So if there's some very convoluted concave surface, and we have those. So okay, I think that's a good refresh point here because now we assume that we have a multiple views, and each of them we have fully a color plus per pixel depth after we've been pre-processing. And now with this data we transmit them, and then we let the user at the viewing side simply do this viewpoint synthesis. Okay, and that raised a very challenging and interesting questions and was tackled by Matthew here, who did that during his PhD at UIUC and now working in Microsoft. So the key observation that Matthew have here is now if we have a depth and a color, and assume that we do pre-processing so that we fill in all the holes, so we have a nice depth map here and the color here. How can we best jointly compress these two images? Right? So of course you can compress the depth and color separately, and but how can we jointly? And the observation we see is someone trained as a waveless and coder here. Most of the bits was spent on encoding the edge, the locations, right, the significant coefficient. And what the two things share in common here is really along these, they have the same edge, right? And again, when we do the synthesis, we really use a edge of the color to guide how to perfect the edge of the depth. So they are sharing the same locations. So that we want to use that, and also we want to show later that having explicit depth location here also help the synthesized reconstruction, the synthesized viewpoint, the view synthesis. Okay, so given these two images, or there can be a video sequence, but let's say we consider this as coding them as an iframe. Then first we detect the edge point, and then once we have this edge point, we only save them once. So we code them using a chain coding, and then using that, we can efficiently encode the color and the depth, given that edge information. So the idea is very cleverly constructed by Matt. We look at the lifting scheme, and the lifting it is an efficient way that people use in JPEG 2000. Is you have a sequence of samples here, so think about one scan line of the image. And you have a set of pixels here. We partition them into odd and even, and the odd sample can be predicted by the even sample, by the two nearby, and through that prediction, and we subtract them, so those pixels tend to be very small, and then we can iterate that several layers, so that over here more of the coefficient would be 0 or small, and then very few are going to be significant. So that's how we can get the energy compaction. Now the key trouble here is, now we do that, typically it's a whole line of the image, but now we only look at this scan line. So we go along here, and that's here the breakpoint, and then another point here. So now along this one here is a very nicely approximated by a low order polynomial, so that with the lifting scheme, a lot of coefficients will go to 0. But then when they have the edge point here, that's going to significantly give us high magnitude coefficients. So how can we eliminate that? Given the knowledge that we know exactly that is the edge location. So the idea here is, when we do the lifting here and we want to just locally extend that area, and these are the pixels that we have to insert them in. And the way that math can find out is simple. Because we model signal as a polynomial, we can easily extrapolate those pixels and turn out there's a very nice closed form formula for that. And we can just insert them here, and those pixels, they are computed by this existing guy here. And based on that, then we have a lot of other coefficients. We go to 0, no significant one. So that was a key idea, and just zooming this depth image. So this, for wavelength, it would be an ideal image model to compress. Even though with that, at a very, very low bit rate, we see a lot of these, compression artifacts. Now, if we spend some bit, it would take that overhead away of coding the boundary here, and then the remaining bit we spend on coding the coefficient. Now, because of this exactly edge locations, we know those where to go to 0. So we have a lot of coefficients going to 0 now. With the same bit rate, we have a much higher decoded image now. Okay. Now what does it mean? Well, taking this, so here's a zoom in version here. What does it mean is taking this per pixel depth, a different viewpoint, and now we synthesize novel view. Then because of all of this nasty edge point here, when we synthesize them, it would create those visual artifacts. Now, with the nice edge that we can encode it efficiently, then the synthesized viewpoint now have a much better quality. So that the gain in coding now turn into the gain in the visual quality. Okay. So let me come to the final project that what we've been working on is we recognize that certain depth cameras. So this is one of these Mesa Sweet Ranger camera. It's bulky, it is a prior connect error. Very poor quality, poor resolutions. But then the color camera is a cheap. We can get a HD color camera. We stick them together, and the question is, how can we improve the depth measurement from this, right? So you can see that if we have a connect, that will be exactly the same setup. A color next to a depth, fully registered. How can we now provide an enhanced depth image? So let me just go directly to the algorithm. The algorithm is very simple. We try many different approaches, and this problem also been looked at by many other research groups. So the one that we found work best is what we call as the joint global mode filtering. So the idea is the following. So assume that we have a color x pixel p here. We have a color value. We have a depth value of that, and we want to enhance them now. And so there is a guided signal. So the depth and the color value here, and this function g here is just Gaussian, so it's a localized. If it is small, so if this thing here go close to 0, that have a high value, and if it's this they have a large difference, then this small value. So it gives a sense of like weighted. If you work on bilateral filtering, this is a thing that you see that pop up on everywhere. And what we got weighted on is, how similar these two guided signal, how similar in terms of location these pixels, and then look at this value. And then we build up this histogram, and then we just find out the max value. All right, so maybe explain by figure here, and just give a sense that algorithm actually is very simple. So imagine that I have a noisy or low resolution depth map, and I want to know at this pixel P here what that depth have to be. That pixel P here can be one of the existing location or the one that we don't know because we want to upsample. And we just simply look through a window around that, and each of those pixels we know what the that have a known depth and color, and then we move them over. So if this guy has a very similar color or very close by, then collectively they have some high weight, and so that we have that weight. And then we do the same thing with the other pixel, and then we collectively we build the histogram for that, and then we just sum them up, and we have a function using that weighted, and then we have that function, and then we just pick out the max. Right? So that's a simple idea. It turned out that what we solving did, some analysis, it showed that the joy bilateral upsampling, which is the bilateral filter version of combining with depth and to upsample being proposed before, it is simply an L2 minimization of this function, whereas this one here becomes just L1 minimization, and we found that it's much more robust and much more accurate. So example results show here. So here is Dongbo, so holding some image here, so they have a color, the depth is of poor quality, and this nearest neighbor interpolation. So you can see that a lot of these artifacts, and joy bilateral upsampling can do this. When you're zooming in, there's those, because of this L2 averaging, as you can, L2 minimization, you can see that it's, get this guy blurring. L1, as we know now, it gives a very robust estimation, and it's, gives sharp edges. And people also propose, they go very expensive using 3D, which is combining different plane swapping, but much more expensive than what we have here, but still cannot compete with this visual quality. So that's what But then one more thing we realized. Is any question? Okay. So one more thing we realized is, well, we can do that well per frame. But then when we play the video, one thing we learned, which has now become another major topic in my research group, is how to exploit this temporal, right? Because remember, we're dealing with not just separate image or frames, we're dealing with videos now. And again, thanks to the depth camera sensors now that they provide us a video rate information. So the question of how to incorporate temporal dependency and consistency is become a very interesting problem now. So just give a sense of a simple fix we do, and I will show the video shortly, is we look at the pixel here, and then let's say we can assume that we can reconstruct this one here, and now we look at the next one here. It might also have a reconstruction, and we first use a very simple look at Canada optical flows, get a simple find out what is the optical flow, and based on the patch similarity, which is a technique now people know in non-local mean, for example, very popular in denoising and recover image. So we look at that patch similarity here and give that a weight, and then from there we can influence what this pixel have to be. So very simple techniques, but to us it worked amazingly well. And I admit this is not the final result yet, but at least give us some insight about how to exploit this temporal consistency. So let me show now So this is the original video that taking the depth map from the low resolution camera, and it simply do nearest neighbor interpolation. Okay, and if we do per frame, then per frame you can see that we have a high quality image, but then it's the temporal consistency here. So you see that per frame it still gives that. Let me play again that video. So you can see those part here, and so the as you can view as the whole video, you see that there's a problem that come up. Now, if we can just apply this very simple techniques in enforcing that temporal consistency, then the edge are much more stable now. But then we also realize that we run into the problem of how to synchronize color and depth, because of this camera that we set up that they are triggered by two different USB. So when the person moving, for example, there's out of sync, so that creates another issue. Okay, so I hope it's not yet a coherent story, but I think that we're just really searching, and as we deal with the real data, we realize that there's more and more interesting open problems. We have to deal with this particular new type of data and sensing device. So let me just conclude by saying that to me, as someone working in signal processing, it is really a paradise, because we have a multiple sensor, we have different modalities, depth, color. Also, I've collaborated with my colleagues in audio part. For example, detecting where is a person, extract the person out, and then we can beamform audio at that location, for example. So this kind of multimodality is very exciting that we can exploit it. And the data is huge, so a lot of data, a lot of computations. Some of the computation have to be done distributedly, right? Because of different node, different cameras, and coupling with communication. How can we compress the data? So I think it opened a lot of very interesting problems for for signal processing, and the applications are really exciting. So that's really make us excited about that. It's been coming a number of papers here. If you want to look at the details of some of the work I present early on. So I want to as Cha mentioned early on, the depth camera is very excited, academic exercise. We play with them, we run them, but then we also realize that, it's going to also change the way people are going to run and deliver visual experience, communications. So 2 years ago, my collaborator and I, we formed together and spin off a company. And let me just, next minute or two, quickly, show you some of the, result we can, develop through that, using the depth camera, and we want to provide a visual experience that, much more engaging, much more present for the people, either remotely giving a presentation or remote collaborations. So you can, there's software that we develop that can be downloaded, try out with the Connect camera. So just let me very briefly show that video, and then I would conclude with a question.
In this tutorial, you will learn to get started using stage presence. So let's go ahead and give it a try. Make sure that your Connect or Nuvixa camera.
So we developed a software that running on a Connect now, something that we would not dream about like 2 years ago, which everyone can buy a camera or Connect. 10 more million units out there. So the person so that's the typical scene here, and we can cut out the background. Of course, that the depth quality from the Connect, it would have a lot of these artifacts along the object boundary. So we use a lot of the know-how how to fix those artifacts. And just showing you an example application, we can extract the person out. Like they can be in anywhere in the office. we can take the person out with a
Once I'm
very
in
nice
position,
clear cut.
I want to make sure that I know where I
And
am
then when we have
the
that,
buttons
we can
that I
drop
will
the
be using on
person
my right.
into
that I can plan my movements accordingly in my
presentations, you know, or you know, you can think about that as a Skype
Alright,
chat
I'm gonna
that
go ahead
I can
and
walk
open my
through some of my
presentation.
desktop
full screen
sharing,
mode
for example.
and go through my presentation as planned. I can simply click on the mouse to move the slides forward.
Yes, so that's the next thing
I'd
because
like
we
to
can now change the eye
Go ahead
gaze.
and
So
tilt the
you're
camera
talking
up a
about like
little
we can correct the viewpoint that the person
Go full
always
screen mode
look
again.
directly. Yes, yes. So
And I
that
can
our
control my
next step.
slides by using these buttons to my right. Make sure
And of
you
course,
practice
you know, we can leverage on the depth that we can do a lot of tracking. So
best
the person can just
you
stand
hold
up
your
there,
hand flat
give a talk.
and gently push forward.
You know, the viewer will see the person be present, interact with the content. Yeah. So you know, what I'm really excited about is now this is a new sensing device. It gives us not just, you know, opportunity
If I'd like to
to
record,
do, you know, research new
I can go ahead
problem,
and
but
go to
also
the record
opportunity
tab
to develop, you know,
and
real
press
new
play if I have a
applications that
microphone, or simply
we
microphone
release
controls
this
can be
we call
used
sneak
with
peek
your microphone.
on our website.
I'll go ahead and start recording.
And instantly, you know, in a month we have more than 1,000
Go to full
downloads.
screen mode
People
again.
try, people, you know,
And go through
do
my
them
presentation
on you know, the typical application
When I'm
thing that we
finished,
try.
I can
You know,
stop
we get
recording.
feedback that people try to do for
And preview what I just
presentations.
did.
People also, you know, upload the video on YouTube. We have people that they
Go to
try
full screen
to
mode again.
you
And
know,
go through my
develop
presentation.
software that
Or I can
people
cut
in
it and save it directly.
rehabilitation, like they want to do the exercise, they see themselves,
also
like, you know,
use this
riding
button right here
bicycles,
to
so on.
upload
They see themselves, you know, on the mountain. So a lot of these very interesting,
so there you have it.
you
Have
know,
fun
potential
exploring the world of
application
stage
could be done
presence. And thank
with
you
these
for watching this
depth-enabled devices. Okay. So with that, thank you very much for the attention. Any questions? Yes, please.
Could you give some detail about how you synthesize the independent view? So is it per pixel?
Yes, we synthesize per pixel. Yes.
So you glossed about there's a surface somewhere.
Right.
How is that surface representation? How do you get there, and how do you get from there back project to the image?
Oh yeah. Sorry. So we assume that the scene, the surface is a Lambertian. So at this pixel we have a color and depth. So depth tells us that, you know, how far that pixel in the scene, and then we go there, and then with that depth information, and we know what the other view, we can, what we call is a propagate that pixel. The color now can copy over to the new view. So that operation that allows us to, with color alone, then, you know, we lost that information, you know, and that's what stereo reconstruction, very difficult challenge. But now if I have a per pixel, the depth information, then I can easily go to the scene and I warp it over here. But after I warp that, then, you know, there's a lot of occlusion, a lot of holes, and that's subsequent steps try to correct for that. Yes.
So you do not try to zoom in or change the position so that you do get no gaps between these spaces, right?
We can zoom in, yeah. So, you know, of course you cannot provide a lot of, you know, zoom in, because then, yeah, as you said, now the density of the new image now must cause, and then we have to do more interpolation to
Make pixels bigger.
Yes, so it is just, you know, it's kind of simple, like just digital zoom. So you see when we do that video, it's not just simply just, you know, changing sideways, but we can zoom in, zoom out. You see that fly through. Of course, you know, if you zoom in too much like a digital zoom, then you start having pixelated.
So you're not trying to build a surface out of your depth point?
No, yeah. We want to avoid that because, you know, the surface reconstruction is a very, you know, expensive operations, and then it also make the problem to be, you know, then it becomes like some kind of computer-generated surface. You know, this one here, we want that, you know, capture this the raw data measurement and just only very simple processing that can be done in real time. Yes.
So notice your reconstruct depths with the arm moving. We have noticed a lot of artifacts around the arm.
Yes.
Is it because of the missynchronization, or it's with the texture image?
Yeah, great. Yeah, it's really the missynchronization between the color and depth. So we have these two cameras that each of them, you know, just give us 30 frames per second video, and then we just take the, you know, the there can be, there's a jitter or the skew between these two. And then we just pick, one color and one depth. So when the object stays still, then there's no problem. But when there's moving here, so for the depth, the hand's here, but the color's the hand over here. Then we have that problems. We know that in the Connect, there's no hardware synchronization. But for the camera, the prime stand we tried early on, it's very simple. If the two cameras are on the same board, they can be run by the same clock and trigger the capturing. Then we can have a perfect hardware synchronization. Then we have less of those problems. Yeah.
Sorry, now that I know that, can you play the temporally stabilized video again?
Sure.
Thank you.
Yes. So let's first see the one without. So yeah. So really the artifact we like to remove is so the like kind of flickering come in and out. But this is when they have a fast motion here, for example, that's going to be a trouble. Okay, so this one here is the nearest interpolations. Okay, so you can see that it's very poor resolution spatially, and the final one, which how can we add interpolation? So yeah, if there's a slow motion, then it's reasonable, but when there's a fast motion, then that's where we have a lot of trouble. But you see, then when there's slow motion here, we can. Oh no, sorry, this is a without the width. Okay, and the without, now you can see that it. It could even worse. So we correct a little bit, but we run into the limit of the hardware. Yeah.
Is there any thoughts to do some kind of software or algorithm-wise to do some temporal thing or something using previous frames?
Yes. So that temporal consistency that we do, which is use is a one attempt. Maybe we have to, after we think about this, maybe we have to not just use one previous frame, but maybe multiple frames. Something that people in coding, they know that multiple reference could get a better prediction, for example. So of course it would improve the quality, but with some of the complexity pay off. But this certainly we was very happy when we see a single image, but then when we play the video, we realize that yes, that's become now a major issue. It's a lot of the algorithm. If you read out there in the literature, just fully focus on this pair of image, color and depth. So I think the depth information now, the ability to capture and record in real time, get this video, I think it creates this interesting new problem. How to enforce consistency across time for the depth video. Yeah.
Another question.
Yes.
To the texture point of view, there are certain areas the depth does not have information, and you mentioned using the interpolation without having any under surface assumptions.
Right.
You do propagation, but what the result eventually, if you have a big occluded area, what the result looks like? It's more curved, or it's more like a plane-like type of thing, given your current interpretation.
Yes, so again, remember there's a picture that we.
You have a ball over there, so if it's more like a curved thing, that curvature continues.
Oh, I see. Yes.
It could also be a plane. So what kind of result eventually, if you did the interpolation, if I would turn it around, we're able to see what it looks like, but there's not showing the videos.
Yeah. We don't have that. Yeah, I think that would be a big challenge. We only, let's say, in a small occluded area, we don't have a color information. That is a very challenging. But now we have a color, and we use a little bit of the guidance from the color, the sharp edge that the color image provides. We can fill in, but yeah, certainly. I think we try. I think if we have a large occluded area, far away, some of the artifacts start showing up. And when you see the video, when, for example, if you the viewing, the fly through, the viewpoint changes, slightly, then we don't see that. But as it's move around, start those artifacts pop up. So I think we have, after that understanding, of course, there's a challenge to go ahead and fix those problems, so that we can have a more flexibility. But also we realize that, if we have a small view corrections, then the technique's quite robust. And maybe the application for that, that's why I show with the real data, if the application is just really video communication, like the typical camera here, and now we want to slightly change the eye gaze so that the camera, the virtual camera behind the scene, directly look into the eye, then that can be done, effectively. Yeah. So not completely free viewpoint, but slightly changed. I think that could be doable. Yeah. Yes.
I have a question about how you synthesize these novel views. When you're rendering a new view, do you warp the depth and color information from a single camera, or do you warp from 2 or 3 nearby cameras?
Yeah, great question. Yeah, we warp from multiple viewpoints. Yeah, and these are already a lot of literature techniques people propose. When you warp multiple viewpoints, then how you resolve the conflict. So again. There's some information from the depth that they can show that which pixel people would use, which one they discard after they warp to the virtual viewpoint, and then some of the techniques how to fill in some of the missing pixels, some of the holes. The reason we use more than one view is exactly some question that was mentioned. If there's an object that only single viewpoint, then if there's occlusion, then we cannot. But now there's another one, then hopefully that occlude area would be visible by another point, so then it fill in. When there's a viewpoint that was seen by both, we do some kind robot interpolation so that it doesn't smear out. Yeah. But that technique that there's already well established literature on that. Actually, there's standard effort on how to do this view synthesis, given there's a color and depth, either single viewpoint or multiple viewpoints. Yeah. Yes.
I have a question is depth and color coding, wavelet coding.
Right.
So the example you showed, it looks like a synthetic data, right? So it was the atmospheric clean.
Right.
Yeah, I was wondering, like, real data such as captured by a Kinect.
Right.
Typically, you see a lot of noise, a lot of holes.
Yes.
When you have holes, in your technique, you would, naturally, you would cut it at the whole bandwidth, right?
Right.
So that would ruin your gain.
Yes.
I wonder if you have your test on those real images.
Great question. Yeah, we didn't actually test with the Kinect, but that's why we did the other problems that I showed last, which is try to attempt at exactly the problem you mentioned. The depth is a poor quality, so then when you encode a lot of those noise, and you pay dearly for that. So now, if you have Kinect not just have a depth, but there's a color next to it. And then the color, we can use that color information to fix those, holes, those occluded area. And then now we have a pair of, pre-process. So, the proposal we think is take those raw, let's say, pair of color and depth by Kinect, use the color image, fix those holes, filling those pixels, and have a clean edge map, and then use that process image for encoding. So then we can have both saving the bit rate as well as enhance image quality. Yeah. So yeah, not going to just throw the data directly into the encoder. That would not work.
Yeah, I'm curious just to see if you sort of interpret the hole. I mean, if you do hole filling, you're not going to fill all the holes for sure. Because some holes are going to be big.
Right.
So it would be nice to see in the end how much, whether they still can gain, how much you still gain.
So that for example, that application here, what we show is, let's say one of the objects. You can see that the way we can cut out the object.
Audio in the video.
Yes. Yes. So you can see that we cut out the object boundary very accurate now. And we do that with the Kinect camera. Why? Because we have the depth. But the depth, if you just do that, cut out, then it's very noisy. But we have a color, so we have a technique that do in real time that cut that very nicely out. And we have that now. That information now is available both at depth and color, and then we can use that to do efficient encoding.
like there are source codes. I mean, for this scenario, if you just call out one person.
Right,
but
yes.
What if there's a room,
Complicated scene, yeah.
You're going to have lots of holes everywhere. That's going to be challenging.
So Matt here can elaborate more, but the key is we don't have to find out all those edges. We only find some of the key edges, and that is expensive. And then we just use that information to guide the encoder. The more we have, the better. But you can just get a few of them that already help to reduce the bit rate. Now the rest we have to we have to spend more bits on coding the residual. So like in coding, like video coding, if you don't do a good job in motion estimation, the residual would catch up, or you have a poor quality, but yeah, it is not going to fail miserably, like it's just degradedly. Yeah.
So from a coding point of view, you want to duplicate the data on the other side as good as possible. So
yes.
It seems you have already do some process on the image. So you save some bits, but then your resolution goes up by a factor of 2. So
right.
In the end, it would probably still be better to just transmit a low resolution there and then do the process there.
Great point. Our experience, we realized that upsample. Remember, when you upsample, the whole thing's still a low dimension, a low order polynomial. And even though you can have a very large signal, but if it's piecewise smooth, and we know where the boundary, wavelet would just eat them very easily. So in wavelets, what happened is it do those transforms. So go back to the very low resolution, even much lower than the original, and then the rest of the remaining high frequency, high subband coefficient, they are all 0 or very small. So yeah, it is a kind of funny. You kind of clean them up, but when you encode them, wavelet take care of that piece. So the bit stream, in the end, it's very small. So people actually learn that, you take an image, you clean them up, or, it turned out that it's much more efficient to encode the clean up image than the original. Yeah.
Okay.
Thanks.